As we discussed before, radioactive decay is a random spontaneous process. So it's continuous, but it's also random. And there's no way of predicting which particular nucleus is going to decay next. However, statistically, if we wait long enough and we have many particles, it's highly probable that given a certain time, a predictable number of them will decay. So there is a constant probability of decay, and that does not depend on the quantity of the substance that you have. So another way of looking at this is in terms of half-life. So the half-life is the time taken for half of the total number of nuclei to decay. So in this example that we see here, the red particles are the radioactive substances here, the radioactive particles in my substance. After a period of one half-life, half of those particles will have decayed. Then if I wait another half-life, half again of what I had now was going to decay. Half of the radioactive particles, so half of the red ones will turn gray. Now at this point, again, after one half-life, half of those will decay. This is rounded up. And so forth. So if we're told that for this substance, the half-life, let's say that it's 1 hour. So how long would it take for the particles to fall to 25% of its original radioactive mass? So first we have 100%, which is this case here. After one half-life, so here it would be 1 hour. After one half-life I would have 50%. After two half-lives I would have 25%. So I would have to wait 2 hours. After 1 hour, we would get to 50%, and after another hour, we would get to 25. So if we assume the initial mass or number of particles, radioactive particles, is N0, after the time of one half-life, I will have N0 over 2 radioactive particles. After another half-life, I'll have N0 over 4 after another half-life. And then another half-life, I will divide this by 2 again. It's always half, right? Over 16 and so forth. So we can actually write this as N0 times a half over N. And this is how many half-lives have passed. So if one half-life has passed, this will be 1, so it will be a half. If two half-lives have passed, then this will become 1/4, and then you can get back to any of those. So you can use this if you want to find out the number of radioactive particles, or how many times have you, how many half-lives have passed. And to solve this, sometimes you might have to use logarithms. When we want to measure the decay or the radiation for beta or gamma decays, we need a device called a Geiger counter. Strictly, it should also be called Geiger-Müller counter. So how does it work? We've got a tube here filled with a low pressure gas, and our radiation is going to enter through this thin window here. When radiation goes inside of this chamber, it will react with the gas, and it will ionize the gas. When this gas is ionized, here there will be some supplied power. So when this is ionized, it will feel attracted to the central electrode. And then there will be some difference in potential, in electric potential, and then it can be measured. There will be a pulse traveling here, and then we can detect it. Now, this type of counter does not work for alpha particles because this thin layer is, well, too thick for alpha particles. Alpha particles are the bulkiest ones, right? So you've got two protons, two neutrons. They are very massive. It's the most massive radioactive particle. So it will stop here. So we need a different device, which is called a spark counter. So for this device, a very high voltage is applied across the gauze, and this filament is positioned just a few millimeters under the gauze. Now, when the alpha particle ionizes the air around here, a spark will jump between the gauze and the filament. Hence the name spark counter. Now, this might seem odd to you, but if we get this device and we just have this lying around, it will detect, even if we're just lying here in our rooms or in a classroom, this would be showing us some measurement of radioactivity. It wouldn't be zero. So we do have what we call a background count, because there are sources of radioactivity all around us. So this is due to the background radiation. We've got loads of things in nature which are radioactive. We've got metals or materials which are inside of the earth. We've got celestial bodies. We've got basically anything, even the sun, right? Or, I don't know, bananas. There are loads of things which we use in our everyday lives, and they do have some kind of radiation. Some level of radiation is not damage, it's not a problem to you. The problem is when it's too much, right? So you have your x-rays, you take your medical procedures, right? You go to the doctor, you probably put some lead plate on the parts of your body which you don't want to see, so there's no application of radiation in those parts, but you do use radiation for loads of different things. So up to a certain level it's not a problem, it's just when it's too much or too quick. I mean, too much in a very brief time, in a very short time. So it's all about the rate. So basically, if we get a Geiger counter like this one and we just turn it on inside of a classroom, it will not be zero, it will not read zero, it will read a certain value. It will vary a bit, go up and down, but if you wait long enough, and as you do in physics all the time, you make many measurements, so you can wait several minutes, and then you would notice, oh, it's on average about, I don't know, 10. So you would have this value, and then you would, when you try to detect the radiation being emitted from some source, you would have to subtract this background radiation because it was already there. Background radiation will change, so the count rate, if you use a Geiger counter, it will change depending on where you are. So it varies from place to place. Here you can see some pie charts just describing each of the sources of radiation that we have usually in nature, that we find around us. The unit for this is sievert, SV. And it's a radiation unit that takes into account the ionizing effects of different radiations. Most people, they will absorb about 1.5 to 3.5 millisieverts per year, right? Or year to the minus 1. Mostly from background radiation. There are places in nature where the background dose of radiation is more than 30 millisieverts per year. However, there's no evidence so far that naturally occurring sources of radiation can cause any health or cancer problems.